All right, thank you very much for the introduction, and thank you very much for the organizers for asking me to speak here today. So I'm going to speak over a broad range of topics that sort of summarize many of the questions I've been thinking about for the last 2 decades. So this is going to be a very general talk, and I'm going to discuss 3 different topics in number theory. So one of my primary motivations is the question of explicit class field theory, which has some deep historical roots, going back at least as far as Hilbert's 12th problem, if not before, and through the development of the theory of complex multiplication. In the 1970s, Stark stated a series of beautiful conjectures relating L functions to special values in Abelian extensions of number fields. And of course, I won't say anything about it, but the most famous probably is, special values of L functions conjecture is the Burgess-Winterton-Dyer conjecture. And then at the end of the talk, I'm going to talk a little bit about transcendence theory and a very specific set of questions about determinants of matrices whose elements are logarithms of algebraic numbers. And this shows up in the special values of L functions. So special values of L functions kind of link these various different topics. So let's start very basic. This is a very wide audience, so start with something we all know. So an algebraic number is the root of a non-zero a polynomial with rational coefficients, and the set of all of these numbers forms a field, which we denote by Q bar. And we'd like to understand the set of symmetries of this field, which is called GQ, the Galois group of Q, which is just a set of isomorphisms from this field to itself. And from the modern perspective of representation theory, we try to understand a group through its representations, and that's what the Langlands program attempts to do, is to try to understand all the representations of this group. So the first step in understanding all the representations of a group is to understand its one-dimensional representations, which is tantamount to understanding the Abelianization of the group. And by Galois theory, this quotient, GQ_ab, corresponds to an extension of Q called the maximal Abelian extension, which could be thought of in a much more simple way as the union, say inside the complex numbers, of all finite extensions of Q that are Galois and have Abelian Galois groups. So the simplest example of such field extensions are quadratic extensions. So you could take Q adjoin root D if D is an integer that's not a square. Then we get a field extension whose Galois group is Z mod 2Z, which is an Abelian group. And then the next sort of example of interest are the cyclotomic extensions. So for every positive integer n, you could take a primitive nth root of unity, e to the 2 pi I over n, and adjoin that to Q, and you get a field extension of Q that is Galois and has Galois group Z mod NZ star, group of units in the ring Z mod NZ. And the amazing theorem of Kronecker and Weber tells you that, in fact, that second example gives you all examples in the sense that every example is contained in one of those cyclotomic fields. Okay, so a subfield of an Abelian extension of Q will be an Abelian extension of Q. And the theorem says that every Abelian extension of Q, finite Abelian extension of Q, is a subfield of a cyclotomic field. So you can obtain the maximal Abelian extension of Q by taking the union of all the cyclotomic fields. Okay, so now you want to generalize this when you're not just working over Q as your ground field, but you want to take any number field as your ground field. And so as before, you can define GF to be the set of all elements of GQ that act as the identity on F. And the Abelianization of this profinite group corresponds to a Galois extension of F, an infinite Galois extension, which is called FAB, the maximal Abelian extension of F. And so moving forward, we're gonna just try to describe this extension. And to do so, we're going to need to use the ring of integers of F, which I denote by just O. So when you see O going forward, this math cal O, that's going to denote the ring of integers of F. So this is the set of elements of F that satisfy a monic integer polynomial. When F is Q, the ring of integers is just the usual ring of integers. Okay. So what does class field theory tell us? So class field theory tells us that there's a structure that's analogous to the picture of over Q, where we have these very special fields, Q adjoin zeta n. So class field theory tells us that for every positive integer n, there's a very special extension of F called the narrow array class field of conductor n. And these satisfy some properties that are analogous to what we saw for Q. So they're nested. So if Fn is contained in Fm, if n divides m, and collectively together, they give you the maximum abelian extension of F. So really, it would be great to understand what these fields Fn are. Now, another thing that class field theory tells you is what the Galois groups of these Fn over Fs are. So there are, of course, abelian groups, because that's what we're doing. We're writing down the maximal abelian extension of F. And so I won't tell you exactly what the Galois group of Fn over F is, but I'll tell you what the Galois group of F1 over F is. It's the narrow class group of F. And the Galois group of Fn over F1 is easy to write down. It's O mod NO star, so the units in the ring O mod NO, modded out by the subgroup of totally positive units. Okay. So just as an example, when F is Q, then Fn is just Q adjoins zeta n. And so F1 turns out to be equal to Q because Q has a narrow class group that's trivial. And the Galois group of Q adjoins zeta n over Q, I told you, was Z mod n star, which is what you get here. And now you're modding out by the totally positive units, but the only units of Z are plus or minus 1, and the only positive one is 1, so you're not modding out by anything. So you just recover the fact that the Galois group of Qn over Q is Z mod n Z star. Okay. So what is the word explicit? So what I said on the previous slide is what you might call some of the main theorems of class field theory. What does the word explicit mean? So class field theory describes the Galois group of Fab over F. It's sort of the inverse limit of the Galois groups of the Fn over Fs. The goal of explicit class field theory is to construct the field Fab itself, okay, or equivalently each of the fields Fn, using analytic functions that depend only on the ground field F. So we have this in the case where the ground field is Q because I told you what Qn was. So Q adjoins zeta n. You adjoin the nth root of unity. So you can think of that as taking the special value of the function e to the 2 pi ix, where x is taking values in numbers with denominator n. That gives you Q adjoins zeta n. And so if I range over all of Q, then I'm getting all of QAB. So the Kronecker Weber theorem can be summarized in this rather analytic way, where we're taking a holomorphic function in the complex plane, e to the 2 pi I z, and you're plugging in, interestingly enough, the values of the ground field Q into that analytic function, and you're obtaining the maximal abelian extension. So there's an analog of this picture when the ground field is a quadratic imaginary field. So if you consider the field Q adjoined root negative D, where D is a positive integer, then we have an explicit description of the field Fn in that case. So first, to obtain F1, you adjoin the J invariant of an elliptic curve that has complex multiplication by the ring of integers in the number field F, this quadratic imaginary field F. And then to obtain the extension Fn, you furthermore adjoin what's essentially the coordinates of the n torsion points of that same elliptic curve. Okay, there's some subtlety at the primes 2 and 3, and you apply what's called the Weber function, but essentially this is just the coordinates of the n torsion points. Okay, and so what's happening then is these modular functions, the J function, as well as the coordinate functions on this n torsion points, which can be interpreted as some modular functions as well. You're applying their special values. And what values are applying? Well, these are holomorphic functions on the upper half plane. You're applying the values in your ground field F that lie in the upper half plane to these modular functions. So it's a very analogous picture to what we saw over Q, where the role of the exponential function is now being played by these modular functions. Okay, so this is the picture that motivated Hilbert in his famed ICM address of 1900 in Paris. In the middle of his list of 23 problems that have served as motivation for mathematicians for over a century was his 12th problem, where he basically asked to generalize this picture. So let me read some very select quotes translated. So the theorem that every abelian number field arises from the realm of rational numbers by the composition of fields of roots of unity is due to Kronecker. So this is the Kronecker Weber theorem that I stated very early on, that QAB is the union of Q adjoins zeta n as n ranges over all the positive integers. Since the realm of the imaginary quadratic number fields is the simplest after the realm of rational numbers, the problem arises to extend Kronecker's theorem to this case. So at the time that Hilbert was speaking, the theorem of complex multiplication, as I stated it on the previous slide, was not yet proven. But he kind of realizes that it's out there. Kronecker had already done most of the work for this. And he's saying, okay, come on, let's finish this up. So Kronecker had called this his Jugendtraum, his dream of youth, to describe the maximal abelian extension of quadratic imaginary fields, and it eventually got done. But even at this time, Hilbert realizes that going beyond the setting of quadratic imaginary fields represents a fundamental new problem. Finally, the extension of Kronecker's theorem to the case that in the place of the realm of rational numbers or of the imaginary quadratic field, any algebraic field, whatever, is laid down as the realm of rationality, seems to me of the greatest importance. I regard this problem as one of the most profound and far-reaching in the theory of numbers and of functions. Now, I should say, these, as I mentioned, these are very select quotes. So Hilbert said a lot more than I've written here on this slide. He gives a very particular type of answer that he wants, and it's something very specifically analogous to the answers that I gave in the case of Q, or a quadratic imaginary field. So we have a holomorphic function with some transformation properties like modular functions, such that when you plug in special values from the ground field, you obtain the maximal abelian extension. Nowadays, it's probably viewed that such an answer that follows in that very narrow type of answer that was being searched for probably doesn't exist, but we still have the goal of constructing analytically the maximal abelian extensions of ground fields. So in the 1970s, Stark stated a series of conjectures which allowed him to approach Hilbert's problem by looking at special values of L functions. So now I want to move into that, that phase of this talk, which is to describe L functions and how they relate to the question of explicit class field theory. So let's start very basic and remind ourselves what a zeta function and an L function are. So for each non-zero ideal of the ring of integers of a number field, the size of the residue ring is finite, and so we define that to be the norm of the ideal. And from this, you define the Dedekind zeta function of the number field, which is just defined in this analogous way to the Riemann zeta function. So you take all non-zero ideals, and you take 1 over the norm, raise it to the s power. And just like for the Riemann zeta function, this has an Euler product. You can take the product over all the non-zero prime ideals, or equivalently all the maximal ideals of the ring of integers. You take 1 over 1 minus the norm of that prime ideal to the negative s power. So examples, right? So this is all motivated by the case when f is q. In that case, the non-zero ideals are indexed by the positive integers, and the norm of the ideal generated by n is n. So you get 1 over n to the s as n ranges from 1 to infinity. That's just the usual Riemann zeta function. If you want to do another example, that's simple. The ring of integers of q adjoin I is z bracket I. So the set of elements of the form m plus ni, where m and n are integers. We want non-zero ideals, so you don't want m and n to both be 0, so you exclude that pair. And for every other pair, m plus ni, the norm of that ideal is m squared plus n squared. So you get 1 over m squared plus n squared to the s power as m and n range over all these non-zero pairs. Now, of course, you've counted each ideal 4 times because there's 4 units in the ring z bracket I, plus or minus 1 and plus or minus I, so you have to divide by 4. And the amazing thing about this zeta function, so the way I defined it as the sum of a norm of a to the 1 over a norm of a to the s, that converges for the real part of s greater than 1 on the complex plane, but it can be analytically continued to a function on the entire plane with only a simple pole at s equals 1. So the class number formula tells you the residue of this meromorphic function at s equals 1, but using the functional equation, it's somewhat simpler to write the function at s equals 0, right? So this is a form in which I can remember what it says. So the leading term at s equals 0, the zeta function, so which by leading term, I mean the rth derivative divided by r factorial, where r is the order of vanishing of the function at that point, it's equal to a simple ratio of invariance associated to the number field, so negative hr over w. So r, the order of vanishing here, is the rank of the group of units. H is the class number, which showed up earlier. R is the regulator of f, and w is the number of roots of unity. Okay, so the reason, so sometimes, so this is a remarkable formula. It's been a central motivating formula throughout, mathematical history since it was originally proven in the middle of the 1800s. A lot of times people say the reason this formula is interesting is that it relates something analytic to something algebraic, but I think that's a little bit bogus. I think analytic number theorists would be, embarrassed to say that there's anything analytic going on here, right? Analytic number theory is a very deep field of mathematics, and this is like looking at the value of a function at a point. That's not very deep analysis. So what's really going on? Why is this really interesting? Why it's really interesting is that the zeta function was defined locally. We looked at all the maximal ideals and took some really simple invariant, which is the size of the residue field. And we packaged those numbers together in some weird way. We took 1 over 1 minus norm p to the minus s, right? And then we made some function out of it and then looked at the value of that function at 0. And so that local information, which was very simple local information, got packaged together and somehow gave you some global information, something that you could only know if you knew sort of the whole ring. So the class number and the regulator, something about the group of units. So that's really what's interesting. This is a passage from local to global. And I learned this perspective from a very beautiful expository article that was written by Barry Mazur on the passage from local to global in number theory. And so if you think about the Birch and Swinnerton-Dyer conjecture, again, it's not that it's telling you something analytic versus something algebraic. That's not the interest. The interest is that it's telling you something that is deduced from the local information of the elliptic curve, the number of points it has modulo every prime, and it's packaging that together and telling you some global information that it has about the elliptic curve, the rank of the Mordell-Weil group. Okay. Now, we want to generalize this zeta function to what are called L functions. So for this, we need to recall the Artin map. So for this field Fn, as long as you look at these non-zero prime ideals that don't contain n, then there's a special element called the Frobenius element in the Galois group that's associated to that prime p. So I won't recall the definition of that, but there's a Frobenius element in the Galois group to every such prime p, because these primes p are unramified in the extension Fn. And from the information of this, or the association of each prime ideal to this Galois element, it leads naturally to the definition of the Artin L function. So we take the product, again, an Euler product of 1 over 1 minus norm p to the minus s. But now, if you have a character of your Galois group, you can insert the value of that character right in front of this norm of p to the minus s and evaluate it on the Frobenius associated to that prime. And that gives you what's called an L function. Just as an example, if chi is the trivial character, then you recover the zeta function, except that, of course, your product is restricted to, the product was restricted to primes that don't contain n. All right. And now using this Artin L function, Stark stated a fascinating conjecture. So this is an open conjecture. This conjecture will state on the slide. So let's fix an embedding of our field Fn into the complex numbers, and we make a technical assumption that turns out to be very important, but we assume that if F lands in R, then Fn does too. And what this assumption means is that the Archimedean place of F that you're looking at splits completely in Fn. Okay, then under this setting, Stark stated a conjecture, and this was, the original set of conjectures in this realm of ideas was stated in like the early 1970s, and Stark sort of refined it over a series of beautiful papers and I think advances in mathematics. And the rank 1 Abelian Stark conjecture that emerged from that, which was very precise, is this conjecture here. So the conjecture is that there exists a unit in the ring of integers of the extension field that is somehow an L function derivative evaluator. So if you take all the conjugates of that U, and you take their absolute value and their logs, then you take their linear combination in the natural way, sort of indexed by, sort of weighted by the values of a character, then you get the value of the derivative of, the L function of this character. And I should say, we're looking at the value of the derivative because this assumption at the top of the slide about, if f lands in R, then fn does too, that implies that the value of ln of chi0 is 0. So the natural thing to look at when the value is 0 is the value of the derivative. And so I didn't mention what the regulator was, and I probably should have when I was talking about the zeta function, but it's a determinant of logarithms of absolute values of units. So it would be a determinant here. This is like the rank 1 case because it's the first derivative. And so it's a determinant of a 1-by-1 matrix, which is just a number. So it's just the logarithm of a single unit. Okay, so this really comes from the inspiration of the class number formula, where the regulator is playing this really important role. And in this case, where you have a derivative, a single derivative, then Stark expects you to have a single logarithm of the absolute value of a unit. And what's very interesting about this conjecture is it's saying something about all the L functions at once. And so you have all the conjugates of this U weighted by the values of the character. Okay, so there's a technical remark that are kind of small at the bottom that this formulation needs some assumptions, which are very mild. But okay. Now, let me try to link what I've been talking about with L functions to the motivation at the beginning of the talk about explicit class field theory. So Stark's formula can be manipulated to calculate the absolute value of U under each embedding. So maybe I can go back to this conjecture. So the number of conjugates of U is the size of the Galois group G. Okay, but that's also the number of characters chi. So the number of equations you have here is equal to the number of these values that are showing up here, log of sigma, absolute value of sigma of U. You can show that the linear system of equations is invertible, so you can solve them back for log of absolute value of sigma of U for every sigma. Then you simply exponentiate and you get the value of the absolute value of sigma of U. So you're getting the absolute value of U under every complex embedding. Okay. And what one really wants to do is get a formula for U itself and all of its conjugates rather than for its absolute value. If I give you a complex number and I tell you I don't give you a complex number. If I tell you I'm thinking of a complex number and I only tell you its absolute value, then you have a whole circle's worth of ambiguity of which complex number I was actually thinking of. So if you actually want to do explicit class field theory and say, hey, we're generating elements of these extension fields Fn. That was our goal, was to generate these fields Fn. That's great. We have these units U, but unfortunately, we only know their absolute value. We don't know the units themselves. So that's an unfortunate setting question. And I became a little bit obsessed with this when I was an undergraduate, actually. And I really asked the question of, can you propose a formula for U itself? And this represents a gap between Stark's conjecture and the question of explicit class field theory. If we had an analytic formula for U itself, it would give a way of constructing canonical non-trivial elements of these field extensions, which we're trying to grasp. And there's a very rich history of conjectures in this direction. So Wren and Čech have a very interesting approach using Shintani zeta functions towards giving an explicit formula for U in the case where the ground field is a cubic field with one real place and one complex place. Charleroi and Darmon gave a very interesting conjecture about the construction of these units in a slightly different setting. And very recently, Bergeron, Charleroi, and Garcia have a very beautiful construction using the form of the Eisenstein cocycle to give a conjectural formula for these units in the same case of a cubic field with one complex place, but it's from a very different philosophy than the philosophy of Wren and Čech. And this has been generalized to arbitrary dimensions by Pierre Morin, who gave a very beautiful talk on this a few days ago here at this conference. My student Kyrie Black also has generalized to arbitrary dimensions, but building on the work of Wren and Čech. So you can see we have these two different perspectives that allow one to try to construct Stark units for ground fields that have exactly one complex place. Now, these conjectures are wide open, and it would be fantastic if anyone had any ideas on how to make progress on them. Okay, but now I want to move to a setting where we can say more, where the conjectures are not as wide open. So and the idea here is to replace the place infinity with a finite prime p. So we consider a non-zero prime ideal p of OF, and there's an auxiliary prime q you need to take, but it's not very important. It's kind of a technicality. So the interesting prime here is p. And we fix a maximal ideal, which is a Gothic capital P that lives above it in the field, in the ring of integers of the field Fn. So the theorem, so it was originally called, it's originally the Brumer-Stark conjecture, and now it's a theorem, which I proved recently with Mahesh Kakde, Jesse Silman, and Julia Wang, which is that there exists a unit, which is now a P unit. So it's not an honest unit, but it has some denominators at P. It's a P unit, or some valuations at P, maybe positive or negative. But what you gain for giving up the valuations at P is that you get absolute value 1 at every complex place, okay? And again, it's like an L function evaluator, that if you look at the valuations of the conjugates of this U, so these are integers now, then the value of this weighted sum by the character chi is the L value, okay? But so we're now in a setting, we didn't have that same assumption as before, where this is a non-zero, okay? And it turns out to be an algebraic number. Now, you need some smoothing. So the problem is that the right side is clearly an algebraic integer, right? These are roots of unity, these are integers, this is an algebraic integer. This L of chi 0 is not in general an algebraic integer. Deligne and Ribbett showed that if you multiply it by this factor, I should say this was also proven independently by Kazunogis. If you multiply it by this factor, then it becomes an algebraic integer. And then there's the hope that an equation like this might be satisfied. And so again, you hope that there exists a P unit that satisfies this L function equality for all characters chi simultaneously. Now, since you've introduced this smoothing, the left side depends on Q, this auxiliary prime Q that you took. So the right side better depend on Q also. So the unit U depends on Q. And the additional condition you get is that U is congruent to 1 modulo all the primes above Q. And this was called the Brumer-Stark conjecture. So let me say a bit about its history. So this goes back to Stickelberger in the 1890s. In the 1890s, Stickelberger considered certain Gauss sums, which are elements of cyclotomic fields. So you've probably seen Gauss sums before in the proof, undergraduate proof of quadratic reciprocity or something. So Stickelberger was interested in the valuations of these Gauss sums, and he proved that the valuations of these Gauss sums were related to L functions of the extensions of, so the L functions of the characters of Q adjoins zeta n over Q. So essentially what he proved was what I called the Brumer-Stark conjecture on the previous slide for the case of the ground field Q. So in the 1960s, Brumer gave a series of talks in which he proposed that Stickelberger's conjecture, or Stickelberg's theorem, should hold more generally for ground fields that are totally real. The elements wouldn't be Gauss sums, the things that Stickelberger was studying, but there would be some conjectural new units whose valuations were related to special values of L functions. Meanwhile, Stark in the 1970s, so a little bit later in the 1970s, Stark stated the conjecture that I gave earlier in the talk about the derivatives of L functions and the absolute value, the logarithms of absolute values of units. And what Tate realized is that Brumer's conjecture and Stark's conjecture were really the same conjecture, just where you're taking a different place of your number field. If it's infinity, you get Stark's conjecture. If it's a finite prime, you get Brumer's conjecture. And Brumer's conjecture was a little bit imprecise, so it wasn't as clean as the statement of the Brumer-Stark conjecture that I made on the previous slide. And so in fact, it was Tate who stated the Brumer-Stark conjecture, as I stated in the previous slide. It's not called Tate's conjecture because that name is taken. All right, so now let me say a bit about how we proved this theorem, the Brumer-Stark conjecture. So this goes back to my advisor, Ken Ribbett. Also in the 1970s, he gave a beautiful paper, a very short paper in Invenciones about constructions of abelian extensions of Q adjoin mu p, when p is a prime. And so that was a case where he wanted to take sort of the p divisibility of some zeta value and show the non-triviality of some class group. So he had to come up with some framework by which you can connect L functions or zeta functions to class groups, right? How do you do that? So to make this dotted arrow, you kind of go the long way around. So he realized that the way that the L functions show up is as constant terms of Eisenstein series. And then from Eisenstein series, you can produce cusp forms. And this is just the usual thing. Like if someone were to, accost you on the street and say, give me the construction of a cusp form, then I don't know what you would do, but the first cusp form I saw the construction of was the delta function. So you take E4 cubed and E6 squared, and they're both weight 12, and there's one cusp. So you look at the constant terms at that cusp, and you just take the linear combination of those two forms to cancel out their constant terms, and now you have a cusp form. And that's really what Ribbit does. He takes linear combinations of products of Eisenstein series and makes cusp forms out of them. Okay, now why do we care about cusp forms? Cusp forms have Galois representations associated to them. We've been hearing a lot about that this week. And the Galois representations associated to a cusp form are irreducible. Now, what happens is if you created your cusp form in a clever way, by taking linear combinations of products of Eisenstein series, then you might be able to make a cusp form that's actually congruent, say modulo P, to an Eisenstein series. And since the Galois representation associated to an Eisenstein series is reducible, we heard about that also this week, then your irreducible Galois representation modulo P should be reducible. And when you have an irreducible Galois representation that modulo P is reducible, then that gives rise to a Galois cohomology class. Basically, if it's reducible, then it's upper triangular modulo P, and then the upper right-hand corner is a Galois cohomology class. And the irreducibility of the original Galois representation allows you to show that that Galois cohomology class that you produce is non-trivial. And that's called Ribbit's lemma. And then the connection between Galois cohomology classes and class groups in Ribbit's case was basically Kummer theory. And in general, it's some fancier versions of class field theory. Okay, so I do want to say some new features that arose for proving this at p equals 2. So I mentioned that the final paper, which proved the Brumer-Stark conjecture, has 4 authors. Initially, Mahesh Kakde and I proved this where 2 is inverted, so kind of away from 2. So another thing we've heard a lot about this week is how difficult the prime 2 is, and that certainly persists in our setting. So doing the case at p equals 2 is as much work as is doing the case for all odd p. So there's some new features, and this is more recent, so I just want to highlight them. So the reason it becomes difficult in applying Ribbit's method is it's the so-called residually indistinguishable case of Ribbit's method. So Ribbit's method is about constructing extensions, as I mentioned, of one character by another, where we try to look at this cohomology class in the upper right-hand corner. Ribbit's method tends to work well when the 2 characters are not congruent modulo p. Now, what's going on is, in our case, we have the trivial character and an odd character. So they're not congruent mod p for any odd prime, right? Odd means, for a character, means that pi of complex conjugation is -1. So 1 is not congruent to -1 modulo any odd prime. But if p equals 2, these 2 characters could be congruent. And Ribbit's method tends to not work well in that case. And in fact, you can't construct the cohomology class by trying to choose the basis in which it's upper triangular. That, in fact, doesn't work. You need a new method to construct a cohomology class. To do that, we invoked a classical theory called matrix invariant theory, which is sort of an analysis of the ring of invariance when you have matrices acting on a group on a polynomial ring. So there's some beautiful work of De Concini and Processi. They have a book on this topic. I forget the title, but it might actually be matrix invariant theory. And the cohomology theory that you need to use then when you're looking at this ring of invariance, you have to look at the derived functors of this, and it's actually not just group cohomology. You have to use what's called rational cohomology or Hochschild cohomology, which is sort of the cohomology of the algebraic group GL2 rather than just the set of points GL2 of Z. And then some really interesting stuff that comes out is the coastal complex and its generalization by Buxbaum and Rim to determinantal ideals. So these are just some new features that show up that didn't come about in the work for odd primes P. Okay. All right, so now let's get back to the question of class field theory. So now we know these units exist, right? So we have our ground fields, which are totally real, these fields F that are totally real, and we've constructed some special P units in Abelian extensions, okay? Now, you'd like to know if you could write down a formula for these units. And pointer would work. There we go. So I had a conjecture in my PhD thesis. So this is well before we knew how to prove the Brumer-Stark conjecture. I was trying to make a conjecture that was analogous to, you know, this conjecture of Wren and Čech, or the conjecture of Charleroi and Darmon, for constructing these not Stark units, but Brumer-Stark units. And because these are, you know, P units living above a prime P, it was natural to try to formulate a p-adic formula for these units rather than an Archimedean formula. And so building upon Darmon's theory of multiplicative integrals, my PhD thesis was the statement of the conjecture that you could generate the prime U by, well, its p-adic value, excuse me, the unit U, the p unit U. The p-adic valuation would be what was given to you by the Brumer-Stark conjecture. So this zeta of U is shorthand for a partial zeta function. It's not the Riemann zeta function. It's the partial zeta function of the number field. It's whatever is told to you by Brumer-Stark. So this part is not very interesting. But the actual interesting part is the p-adic part of the unit. And it turns out to be an integral, a multiplicative integral in the sense of Darmon, of just the function x. But what's really interesting is the measure that you're integrating with respect to. And so I came up with a form of the Eisenstein cocycle that gave rise to this measure. And the Eisenstein cocycle itself has a very rich history. One can construct it using Shintani's method. So my original method was using the integrals of Eisenstein series in the upper half plane, because I was only doing the case of real quadratic fields in my in graduate school. But later, to generalize to higher dimensions, I didn't know the theory of sort of Bergeron, Charleroi, and Garcia at that time because it hadn't been invented yet. So I used something that was simpler for me, which is Shintani's method when I was a postdoc, to write down a formula for the Eisenstein cocycle and then generalize this conjecture to arbitrary setting. And I'll just mention that there's some very beautiful work of Guido Kings and Bailenson and Levin on the topological polylogarithm, which is another approach to constructing the Eisenstein cocycle. And I have another paper with Charleroi on generalizing Čech's method to construct the cocycle. So there's a really rich history of the Eisenstein cocycle. But the interesting thing is that this is actually computable. Okay, so Renee was asking me if I'm going to have any examples in my talk. So here's a class field for you, Renee. So you could actually, I had some students at Duke plug this into a computer. So that integral, you can actually compute it. And so the ground field is Q adjoint root 305. I wanted to, I picked this because I wanted narrow Hilbert class field that was that has some interesting size. So it's a Z mod 4Z extension, and because of the assumptions, you need 3 to be inert in that quadratic field. So that's kind of, I think, the smallest one with these properties is root 305. And so you just evaluate those integrals. So you get some crazy p-adic numbers when you evaluate them. Some p-adic numbers with you do it to as many digits, maybe 100 p-adic digits. And then you take the elementary symmetric polynomials of those 4 elements that you produce, and then you put them into the coefficients of a polynomial, and then you get something very small coming out, like 9. And then you know that you've gotten something good. You didn't produce garbage from these p-adic integrals. You actually, their sum was an actual algebra, very close p-adically to an algebraic integer. So you write this down. So you get some polynomial. And then you go back and check, does this polynomial, split over, is the splitting field of this polynomial an abelian extension of f that is everywhere unramified? And it turns out it is. It generates an abelian extension, and it's everywhere unramified. It's the narrow Hilbert class field of the field F. And you can do bigger extensions. So here's a degree 6 extension. You can see the numbers get big pretty quick, but that's kind of forced on you by Stark's conjecture, the Brumer-Stark conjecture, because the valuation here is 10 of this unit, because that's what the Brumer-Stark conjecture tells you it has to be. And then, so the other coefficients are about the same size. So. And again, you can check after the fact that the splitting field of that polynomial is the narrow Hilbert class field. So just to be clear, the program to produce this only inputs these two numbers, 473. So you're taking this Q joint square root of 473. You're taking the prime p equals 5, and then you tell it, compute these 6 p-adic integrals for me, and you compute them, and you take their elementary symmetric polynomials, and you get this monstrosity. But that thing turns out to generate the narrow Hilbert class field F1. So this is an actual algorithm now for generating the Abelian extensions of all totally real fields. Okay, and so just to sort of close the loop on this, we wanted the maximal Abelian extension of F, and I told you how to produce certain special elements, these Brumer-Stark units, but it turns out that all of them together do give you the maximal Abelian extension of F. So that's almost true. You take all the Brumer-Stark units and you adjoin some simple square roots. And the reason for that is that Brumer-Stark units live in CM extensions, and you need extensions that are not CM. So you have to throw in basically all possible signatures that you get of a field. And once you do that, you get the maximal Abelian extension of F. So now we've shown the existence of elements, that's the Brumer-Stark conjecture, together with a p-adic analytic formula for those units that together generate the maximal Abelian extension of any totally real field. Now, I don't think Hilbert would have been very happy with this answer to the generation of the class fields of totally real fields because, first of all, it's p-adic. I don't think he was very fond of p-adic. But second of all, it definitely does not lie in the yoga of evaluating special functions at special points. I think there is a philosophy that when you're looking at a ground field that has a unit group of a certain rank, positive rank, then you should expect to make integrals of that dimension, right? And so that's the reason why Q and quadratic imaginary fields were special. They have rank 0 unit groups. A 0-dimensional integral is essentially the value of a function. And so that's why it kind of works in those settings. And the general belief is that for higher rank unit groups, so ground fields with higher rank unit groups, you should expect integrals of that dimension. And that's exactly what my formula is. It's a p-adic integral of that dimension. Okay. Let me just say a few words about how you prove this conjectural exact, prove this exact formula that goes beyond what we did for Brumer-Stark. There's 2 new ingredients that go beyond this. One is an integral version of what's called the Gross-Stark conjecture, which is due to Gross, which talks about how Brumer-Stark units behave in towers. And so basically I showed actually a while ago that that conjecture implied my p-adic integral formula. Okay, and then you have to ask yourself, how do you prove that Gross-Stark conjecture? And the way we initially did it was idea of Wiles, really, and the Taylor, what's now called the Taylor-Wiles method of introducing auxiliary primes, and also goes by the name of horizontal Iwasawa theory. So that was kind of the strategy that we used to prove the Gross-Stark conjecture. Okay, now in the last 15 minutes of the talk, let me connect this to really a completely different branch of mathematics, transcendence theory, which I got inspired to thinking about because of the special values of L functions. So I mentioned that the residue at s equals 1 of the Dedekind zeta function is essentially the regulator times the class group with some other factors that are going to get absorbed into this tilde symbol. And the regulator, as I mentioned, is the determinant of a square matrix whose entries are absolute values of logarithms of units. Okay, as U ranges over the units of U and sigma ranges over the embeddings of your number field into the complex numbers. Okay, so you have to kind of eliminate a certain number of columns of this matrix so that it's square, and then you take its determinant. And it's a very important theory that theorem that the regulator is non-zero. And the way you prove that is via some geometry of numbers argument. You have sort of Dirichlet's unit theorem, which is proved by embedding the units into some Archimedean space, and you can show that the image of that embedding is a discrete subgroup of of the Archimedean space that you've embedded into, and that's equivalent to the regulator being non-zero. Now, there's a p-adic analog of this picture that is actually wide open. So it's a very important and beautiful theorem of Kolmez that the limit as s goes to 1 of s minus 1 times the p-adic zeta function is essentially a p-adic regulator. Okay, a p-adic regulator means a determinant of a matrix of p-adic logarithms of units. All right, so we don't know that there's actually a pole. I said residue at s equals 1. We don't know that there's a residue. We don't know that there's a pole of this because we don't know that this is non-zero. Okay, if this is 0, then somehow this would be regular at s equals 1, which would be a very odd thing for the p-adic zeta function to not have a pole. So we don't know this is non-zero, and this is a conjecture of Leopold that was maybe stated in a slightly different way in terms of using class field theory in terms of Abelian extensions, so sort of ZP extensions of ground fields and what the rank of the maximal Abelian ZP extension of a certain ground field is. That's related to, that's equivalent to the non-vanishing of this regulator by class field theory. And this regulator, we have no idea how to prove that it's non-zero. So I started thinking about this. So more generally, I started thinking about the question of, let's just take a matrix of logarithms of algebraic numbers and ask what its rank is. So the very simplest example of a conjecture in this direction is known as the 4 exponentials conjecture. So consider a 2 by 2 matrix of logarithms of algebraic numbers. So log A, log B, log C, log D. And assume that the determinant is 0. So log A, log D minus log B, log C equals 0. Right? And by the way, we don't know this conjecture even if A, B, C, and D are just integers. Take them to be positive integers. This question is wide open. The conjecture is that if the determinant of that matrix is 0, then neither the rows or the columns of M are linearly dependent over Q. Okay? So now you're saying, isn't that linear algebra? Well, no, linear algebra says they're linearly dependent over C. The rows are and the columns are. But we don't know that they're linearly dependent over Q. All right, and so you can make a very similar conjecture over the p-adic. So if you just put log p here instead of the usual Archimedean log, you put the p-adic log, you have the same conjecture with assumptions about maybe A, B, C, and D need to be 1 mod p in that case. And that's wide open. And so knowing this would imply the 2 by 2 case of Leopold's conjecture, where you have a 2 by 2 matrix, the p-adic version. But we don't know how to prove this. So what is the approach to this? So sort of more standard approach to this is using the theory of auxiliary polynomials. So what you do is, let's consider, okay, so these are the same A, B, C, D that were in the previous slides. So I had my matrix log A, log B, log C, log D. So let's take the vector AB and the vector CD in Q bar stars squared. And let's look at basically the subgroup generated, the subgroup of Q bar star squared generated by these vectors x1 and x2. And we define what's called a box, which is you just take all the, the powers, so all the elements of that subgroup, but you only look at the elements where the exponents are between 0 and n minus 1. So if they're generic, if there's no overlaps, then this should have size n squared. Okay? And the classical approach, maybe what do I mean by classical? Well, maybe I'll say what I mean by that in a bit. Classical usually I tend to find means that it was done before the person speaking had thought about the problem. But in this case, classical does go back at least to the 1960s, if not before. The idea would be, what you want to show is that if the determinant of this matrix is 0, then for n large enough, there exists an auxiliary polynomial, so some polynomial in 2 variables, that has degree less than n and which vanishes on all the points of this box. And maybe just to give yourself some extra running room, you make it vanish on twice the box, so the box of size 2n. And why would you expect this not to be the case? So there's roughly n squared monomials of degree less than or equal to n. And so, saying that they vanish on a given point is a linear relation on the coefficients of that polynomial. So you have kind of n squared linear relations, but you're imposing now, 4n squared conditions, so you don't generically expect that system of equations to have a solution. So if it does, then you can prove that the four exponentials conjecture is true. So if you could construct this, right? So somehow, like if the columns of your matrix were linearly independent over Q, then there would be a polynomial of bounded degree that vanished on all of X. And so this would certainly be true. And if the rows were linearly dependent over Q, then the size of X of n would collapse and be linear in n rather than quadratic in n. So then by that linear algebra argument that I gave you, you'd find a polynomial. So that's why you'd expect, if the theorem that you're trying to prove is true, that this polynomial would exist. But it turns out that you can prove it. And it's basically Bézieux's theorem, right? If you take a polynomial of degree n and you kind of shift it by one of these elements, xi, then that's a new polynomial that still vanishes on maybe x of 2n minus 1. And so they overlap in all of x of 2n minus 1, which has size quadratic in n. So, size 2n minus 1 squared. But you have two polynomials of degree n, so by Bézieux's theorem, they should intersect in n squared points. So you have sort of 4n squared points of intersection when Bézieux's theorem says you should only have n squared, right? Now, to make that rigorous, you need to make sure that when you did this shifting, the two polynomials intersected transversely. They didn't have a common factor. And in order to prove that you can do that with some shifting, that's why you give yourself this extra room here. Okay, so it basically boils down to Bézieux's theorem. And I should say, this methodology was used by Waldschmidt and Masser in a rather amazing pair of papers to prove what's now the strongest known partial result towards Leopold's conjecture. So they were able to prove that the real Leopold matrix has rank at least half what it's supposed to have by using a generalization of this technique of constructing polynomials with bounded degree that vanish on a box that's large enough that it shouldn't be able to do that unless there's some genericity that's violated and you actually have extra dependencies. Okay. Now, my philosophy is that, in fact, to prove the four exponentials conjecture, I don't think this is the correct approach, this exact approach. And to understand why it's not the correct approach, I want to talk about what would the generalization of the four exponentials conjecture be. So it turns out that the naive generalization, that if you have an n by n matrix of logarithms of algebraic numbers whose determinant vanishes, then there has to be some linear dependence over Q of the rows or the columns. That turns out to be false. And I can give you a simple proof of that without even writing anything down. We'll just take a 3 by 3 skew symmetric matrix and assume that the non-zero entries are just logarithms of independent prime numbers, say log 2, log 3, log 5, for the non-zero elements of this skew symmetric matrix. Since it's skew symmetric, it has determinant 0. It's a 3 by 3 skew symmetric matrix. But you can show that if these primes are, you take independent primes, then these are, the rows and the columns are linearly independent over Q. So that's not going to be the conclusion you're going to draw from a matrix that has vanishing determinant of logarithms of algebraic numbers. So what is the conclusion that you can draw? So this was, okay. Sorry, so I got ahead of myself. Let me go back. I'm going to go forward and then back. So what is the conclusion you can draw? So this is this conjecture I stated jointly with Mahesh, which is that if you have an n by n matrix of logarithms of algebraic numbers whose determinant vanishes, then there exists non-zero vectors w and v such that when you multiply them on the left and the right by this matrix, that you get 0. So in other words, a fancier way of saying this is that you could change bases rationally for this matrix and some coefficient will then be 0 in the matrix. Okay, that's why you call it the matrix coefficient conjecture. And okay, so let me say these theorems in reverse order. So there's an uber conjecture in the theory of, transcendence theory of logarithms and exponential functions called Chanuel's conjecture, which is way too hard for me to even think about. But it's believed to be true. It implies Leopold's conjecture, for example, and the four exponentials conjecture. And it implies something that's even weaker called the structural rank conjecture. The structural rank conjecture tells you if you have a matrix of logarithms of algebraic numbers, it tells you exactly what the rank of that matrix should be. Basically says take a Q basis for the entries and then replace those basis elements with formal variables, and whatever the rank of that matrix over the ring of formal variables is should be the rank of your matrix. Okay, so basically all dependencies are explained in terms of linear relations amongst the entries. So that's the structural rank conjecture, but even that I think is too hard to approach. That actually turns out to be equivalent to a special case of Chanuel's conjecture that was proven by Damien Roy. So I think that's a really hard conjecture, and that's too hard. But what's really nice about this conjecture, it's much simpler to state, and it's implied by the structural rank conjecture. So I believe it to be true because it's implied by conjectures that are assumed, to be true in the literature, but very hard to prove. And I hope that this matrix coefficient conjecture is a little bit simpler, but it's still very strong because it implies the four exponentials conjecture, it implies Leopold's conjecture, and it implies the Gross-Kuzmin conjecture, which is about the p-adic vanishing at s equals 0 rather than at s equals 1. There's a regulator that shows up there that was constructed by Gross. Okay, so what is the approach that one should take in terms of auxiliary polynomials to study this conjecture? So my initial guess about this, and let me go back now. My initial guess was to relax the condition about the degree of the polynomial that you're trying to construct that vanishes on this box, and to make a polynomial that has fewer than n squared monomials, so fewer than n squared non-zero coefficients. So obviously any polynomial of degree n satisfies this condition, right? But it turns out that you don't need it to have degree less than n. It could have an x to the 3n over 2 term, or even an n to the x to the n squared minus 1 term or whatever, as long as it has fewer than n squared monomial involved, right? There's no bound on the degree in this conjecture, right? So, and it turns out this implies the four exponential conjectures over R over CP. And I haven't been able to prove it over C. I'm not sure if it's true, but I sort of quickly realized when I was trying to generalize this to higher dimensions that even this is probably not the right formulation, even though this is very, very soft condition on the polynomial. I don't know how to produce it, okay? It would imply, amazingly strong results, four exponentials conjecture over R. So for example, for integers, what I talked about earlier, that it would give the four exponential conjectures over for integers. But yeah, we don't know how to construct this. But what I realized is that when trying to generalize this to higher dimensions, that this property of having few monomials is doesn't behave very well in algebraic geometry. So I started studying the theory of funomials. And when I learned about it, I realized there's a more robust theory that's due to Bernstein and Kushnarenko. Oops, what was that? Oh my God, I'm not sure what's happening. Okay. Oh, is there a fly? Yeah, there was a fly landing on the screen earlier that was messing things up. Okay. Okay, so it turns out that you don't need to use Bézou's theorem to bound the number of intersections of two polynomials. And so I want to give you an example. So let's say that you're considering a polynomial like 4x squared minus 5y cubed plus 2x cubed y squared. Then it turns out that what you can do is just plot the coordinates of the exponents. So 2, 0, because there's x squared y to the 0 here, so 2, 0. And then y cubed gives me 0, 3. And then x cubed y squared gives me 3, 2. And so you notice I've ignored the coefficients. I just took the monomials, exponents. And then what you do is you take the convex hull of those points. In this case, it's just this triangle, because I have 3 points. And you take the area of it, and you multiply it by 2. So that's what delta is. Delta is the convex hull of the monomials that show up. And you take the volume, and this works in any dimension. I'm just drawing the picture in 2 dimensions for a simple example. But you take the area here and you multiply it by n factorial in general. So here you multiply it by 2. So this has area 7. Now it turns out this is an amazing theorem. If you take 2 polynomials that have the same monomial support, so okay, So here's another polynomial that has the same monomials that show up in it. Then the number of intersection points in C star cross C star is exactly twice that volume. So it's 7 in this case. And that seems crazy. If you think about this to me, this looks great because this has degree 5 and this has degree 5. How many points in projective space do these equations intersect in? 25. 5 times 5. Okay, but you're getting a much smaller bound on the number of intersections C star across C star. And you see what happens is if you projectivize this, so you put in, Z cubed and Z squared here, and you look at their points of intersection, they intersect at 0, 0, 1, 0, 1, 0, and 1, 0, 0. So points where some of the coordinates are 0. And they intersect at each of those 3 points with multiplicity 6. So there's 18 points of intersection that you're missing. And that's why you actually get 7 in the plane. Okay, so this is a much different way to bound, and in some cases, stronger than Bézout's theorem. And I should say there's a generalization where they don't have to have the same monomial support for this theorem. There's something called a mixed volume of 2 different polytopes rather than the volume of 1 polytope. Okay, and so I think I'm going to basically end. Lost it. What timing? Yeah. Okay, can I go forward? Okay, thank you. Okay, so given n, so this works in any dimension, and we can define the Bernstein-Kushnarenko number of n polynomials and n variables as just n factorial times their mixed volume. Okay, and then because of time, let me just. So you need to bound not just this volume, but you need to also replace sort of for a given polynomial, sort of with a generic linear polynomial. But the auxiliary polynomial that I think you need to construct is a polynomial whose degree, in the sense of Bernstein-Kushnarenko, there's the volume of this polytope, basically. That's basically what this is saying. Has to be bounded by n to the n, and it vanishes on the box of, nn. And that polynomial turns out, that conjecture, the existence of this auxiliary polynomial, turns out to be equivalent to the matrix coefficient conjecture. So this matrix coefficient conjecture, which we assume to be true, can actually be shown to imply this exists. And, but the deeper thing, which we proved, is kind of an analog of Masser's theorem, is that this existence of this auxiliary polynomial actually implies the matrix coefficient conjecture, which in turn implies Leopold's conjecture. So I should say it's an honor to be speaking about this in front of Michelle Waldschmidt, who's chairing this session, whose work was very profound in getting us in this direction. We never would have had any of these ideas if not for his work. So thank you. I'll end there. Thanks.